Okay, so last week we were talking about something that we called an annuity. So let me kind of scroll up here. Okay, so we started off doing the compound interest. So that was a formula that could be used if there was just an initial lump sum that we put away kind of in a savings account, or something that earned interest, right? But it was a very kind of stripped down problem where we had this large sum of money and it was put away, and then there was no extra withdrawals or deposits made. Now that's not really a realistic formula most of the time, right? Sometimes we might do that. We just have a large sum of money and we just put away and essentially forget about it. What is a little bit more realistic is that not just one large sum of money, but you kind of make periodic deposits, right? Monthly, right? Every 2 weeks, every 3 months, etc. Right? Something like that, where you are depositing a certain amount and you're earning compound interest as time progresses, right? Not just one time. But you have compound interest, and that compound interest is being earned not just for the previous balance, but as you deposit, that money is also earning interest as well. All right. So think of, you set yourself up a savings plan, right? And then as soon as you make your initial deposit, you start earning interest on that amount. But each time that you make your time deposit, like if it's once a month, for example, then that new balance starts to earn interest as well. All right. And to kind of model that is this annuity formula that we see in front of our screens there. All right. And that is able to calculate how much money would be at the end of whatever number of years. Okay, so and again, today we're going to introduce another formula. So you always want to ask yourself when you start solving these problems is which formula do I need to use, right? And that is going to depend on if it's one initial deposit of a large sum, or whatever the sum is, then it's going to be a compound interest. If there are many deposits, then you're going to use the annuity form. Right? And two examples that we did were, we looked at retirement accounts, and if we saved $100 a month, how much would be in there after 20 years, right? So we did here a basic one here. And then we looked at, well, let's say that I had a goal in mind. I said, all right, my goal was to save $1.5 million by the time that I retired. And we looked at two different scenarios, right? One where we started saving when we were 24, right? And if we did that, we calculated, all right, I'd be able to reach that goal by saving $631.21 for each month. And then we said, all right, what if we change the problem up a bit, where our goal is still $1.5 million, but now I started 11 years later at age 35. And we saw that almost doubled, or more than doubled, what our monthly deposit should be. Okay, so just to kind of get an idea how this compound interest kind of works, right? So it's not exactly a linear path where we went 11 years, it'll take us an 11th more to do that, right? It actually would be slightly more than that, right? Because the larger your balance is for the longer time, that interest becomes more and more. Okay, but today we're going to take a look at, well, what happens at the end, right? Let's say you're ready for retirement, right? What do you do with that money? Do you just you close out your retirement account, but you don't just put it, or you shouldn't just put it in like your checking account, right? If you have that 1.5 million, right, you don't just want it sitting in a checking account, right? What you would like for it to do is to sit in an account that, even though you're retired now, that account is still earning interest for you. Now you withdraw a certain amount of money to get by each month, right? Kind of your fixed income. All right, you say, all right, I'm going to live off of this much money each month, and the rest of it is kind of stored away in an account that is earning interest as it just sits All right, now that type of situation is called a payout annuity. Okay, so so when to use. All right, so we're going to use this when we have many withdrawals. And no additional deposits. Okay, and as you notice here, there is it looks very similar to our regular annuity. All right, if we kind of, let me scroll up here. Let me see. All right, our regular annuity formula looks like this. All right, and we see it looks kind of the inverse of it, not quite the inverse, but just kind of the opposite of what we want to do is withdraw instead of deposit. All right, and we see that kind of switches up our formula a bit, right? All right, we switch the order of the difference, and then the exponent becomes a negative exponent. Okay, so whenever we have some type of we have an account where we're kind of withdrawing on a regular basis, right? We're going to use this payout annuity, right? So think of, you have this large sum of money, right, from your savings, and now you're going to live off of those savings, right? And what you do is you put it in what is called a payout annuity account, where you can withdraw, let's say, on a monthly basis, but that rest of the money is still earning interest, right? And here the opposite effect happens, that as you withdraw the money, it's earning less and less interest because there's less money in there, right? And there's no additional deposits being made, right? That initial amount is just kind of sitting there, it's fixed, right? And then after that, it just keeps dwindling down, right? So let's take a look at an example, right, of using this formula. Okay, so in this example, it says after retirement, you want to be able to take $3,000 every month for a total of 25 years from your retirement account. The account earns 6% interest. How much will you need in your account when you retire? Okay, so here is a kind of a plan here for retirement. You plan to live at least 25 years past the date of your retirement, right? And you are able to, if you made the calculations, figure out you're able to live off of $3,000 every month. Okay, let me bring back the formula from above here. Let me write it up here. So our annuity formula is P0 D 1 minus 1 plus R over K to the negative NK. And all of this is going to go over R over K. Okay, now similar to the annuity formula, the non-payout one. So D is, in this case, how much we plan to take out every month, right? Instead of the deposit, D represents the withdrawal, right? So in this case, we're aiming to take out $3,000 each month. All right, and the, excuse me, N, capital N represents the number of years, and we are planning to do this for 25 years. And then the other number we see there is the 6% interest. So we'll say, all right, that one is always easy to identify, right? The rate is going to be 0.06. Excuse me. Okay. Now, one thing that is not explicitly told to me here is what the value of K is, right? And as a reminder, K is how often the interest is compounded, right? And again, if it's not stated, right, and here it is not, we're going to kind of, we're going to make the assumption that how often I take out money, that would be how often the interest is compounded, right? So by kind of assumption here, we can assume that K is going to be 12 since withdrawals are made monthly. Yeah, every month, right? Yes. All right. So again, if it doesn't say explicitly how often the interest is compounded, just assume that it'll be the same amount as how often you are withdrawing from the account. Okay. All right. So now we've identified all the little pieces of information, right? What I don't know is the P0, right? How much money I should start off with. So what I don't know is this, right? P0 is we need to find, right? And again, right, for problems like this, we'll always be in search of something. So one of the variables is going to be unknown, and we're going to need to find. All right. So we need to find P0, or in other words, how much money do I need to begin with? How much money is needed to accomplish this goal, to have $3,000 a month for 25 years, right? In an account that earns 6% interest. All right, so let's see here. So P0, and let me write out my formula here with all of the variables that I know substituted in. Okay, and then down here. All right. Okay, any questions so far on the setup? Oh, excuse me, I forgot. N is 25, K is 12. Okay. So now we've kind of written out our formula here. I'm sorry, Theodore, what are you, what are you referring to? I know my writing is a bit off here, but let's see here. Since this is so K is 12, since withdrawals are made monthly. Okay. All right. So now once I have my formula kind of written out, the next thing is, well, how am I going to substitute this or write this into my calculator, right? So let me bring up my calculator here. Okay. And we'll start off, we'll put the 3,000. I'll open up my first parentheses there, and I'll write 1 minus, and then I'll open my second parentheses. All right, and there I'll put 1 plus 0.6 divided by 12. All right, and then I'll close that second parentheses, and I'll use my caret, right? Raise it to the power, and again, be careful here. Make sure, now the nice thing about this version of the calculator is that when you hit the caret, it automatically puts you in the exponent. Some later versions just give you the actual caret symbol that you see there, that little arrow pointing up. In which case, if you're going to write an operation there, make sure you enclose that operation in its own parentheses. Right? But here I don't need to worry about that. I can simply plug in negative 25 times 12. Right? And then from there, I want to get out of the exponent. So I'll just hit the right arrow down here. And that brings me down from the exponent. All right. And now from there, I'm going to, sorry. All right. I hit the wrong button there. Let's try that one more time. All right. So 3,000. Oh my goodness. 3,000 times 1 minus 1 plus 0.6 divided by 12. And this is going to get raised to all right. Sorry about that. I'm going too fast here. Okay. So we have that. Now let me bring in the caret. And then from here, I'll plug in negative 25 times 12. And then I'll get out of the exponent. I'll close my parentheses. And from here, I'm going to hit divide. And here, be careful. What we're going to do here is, if I want to make sure that this is done properly, where I divide by 0.06 over 12, I'm going to open up another set of parentheses for the denominator and plug in 0.06 divided by 12, and then close it. Okay, and now I have all of my formula in my calculator. Right, so scrolling back here, you see, okay, so here we have the 3,000. I open up my parentheses, 1 minus, I put the stuff inside the inside parentheses, then the exponent, and then the close parentheses, and then divided by R over K. All right. And now I'm going to hit enter. Okay. And then I arrive at this, this solution. Right? So that means that in order for me to live like this, off of $3,000 a month for 25 years, in of course, an account that earns 6% interest, I would need to start off with the following quantity, $465,000. So let me switch over here. So we have P0 to be $465,000, 620 with about 59 cents. Okay. All right, so we would need that much amount there. All right. And again, of course, if you would like to, now, if you would like to make this last longer, right? But still have 3,000, then it would be more, it would clearly be more initial money that we would, right? So again, just remember that for something like this, there would be no more additional deposits, right? Once you're there, you just have that lump sum of money. But again, right, it's in an account that earns interest, but eventually all of that would go away, right? So this would be the minimum to live off $3,000 for 25 years. 5 decimal places. Well, I just went 2 here for money. I mean, if we're dealing with money, yeah, annually. Uh, what do you mean by annually, Renee? Yeah, if we're dealing with money, then 2 decimal places just to go to the nearest cent is usually more than enough. Right? I always do that when I'm working with money. All right. Renee, can you explain? Okay. All right. All right. Any other questions here? All right, but we're all clear now, Renee? Okay. All right. So here. All right, so there's no questions. I'll move on to our next example here. So for this example, it says you have managed to save $1 million for retirement. You plan to withdraw $2,500 a month from an account that earns 5% interest. For how many years will your retirement fund last? Okay, so something like this. So we're solving for the amount of time. Excuse me. All right. So let me bring the formula up here. Okay. All right. Now we in order for us to solve, now notice one thing that we have to well, one thing that pops up here is that we're solving for uh, capital N, right? Now, if we go through this, let's kind of decipher all of these variables, the numbers that are given to us and what they represent, right? So it says you have managed to save $1 million for retirement, right? So you have, okay, that is how much I start off, right? I've retired, I've worked very hard for my money, and I have $1 million to last me into my retirement. Okay, and it says that you plan to withdraw $2,500 a month. All right, so our withdrawal each month, right, a month is $2,500. All right, from an account that earns 5% interest. Okay, so I have that, and if it's a month, so we're gonna assume here that the account earns interest at the same time that I withdraw, or at the frequency, I should say, as the how often I make withdrawals. All right, so I'll let K is equal to 12, since withdrawals are made monthly. Okay, now the one thing I don't know, right, is N, right? If I have this set up, how many years can I live off of this money? All right. Now, we need I guess a new tool to help us do that, right? Something that we haven't talked about up to this point, right? So as you'll notice here is that our unknown is in the exponent, right? So if it was, that's a lot different than all of the equations we solved up to this point, right? And let me actually, why don't we start solving it, and then when we get towards when we need this new tool, I'll bring it up, right? But for now, let's plug in what we know into our equation. So our P0 is 1 million. D is equal to 2,500, and then times the rate is 0.05, and then here K is 12, and then in my numerator, excuse me, in my exponent, we get negative N times K, so negative 12K. 12N, excuse me, K is 12. And then down here, we'll have R 0.5 over 12. Okay. All right. So here is our setup, right? And again, notice here the big difference here is that that value for N is in our exponent. Okay. Any questions up to this point? Up to this point here. Okay, so if we want to solve for N, we need to isolate the N, right? So that it doesn't change, right? That is the same kind of process as solving any equation, right? Our goal here is to, in this case, what we want to do is isolate N. Okay, so the first step in doing that is, it looks really complicated, so let's start uncomplicating these things. And the first step here would be, if I have any kind of fraction, let me get rid of the fraction first, right? And the way I do that is by multiplying both sides by whatever the denominator is, right? So I'm going to multiply by 0.05 over 12 on both sides of the equation, right? 0.05 over 12. All right. Use parentheses to avoid confusion here. All right. So when I do that, notice that on the right side of my equation, this is going to reduce to 1. All right. So my right side becomes 2,500 times 1 minus 1. And actually, let me do another step here. Let me add these two numbers here, right? Just so I can simplify. So I don't have to keep writing 1 plus whatever. Let me find out what that whatever is, right? 0.05 divided by 12. And that is 0.00417. All right, I've rounded here. I chose 5 decimal places. Now, if I'm not dealing with money, to avoid, so whenever the result is not money, remember, I always choose 2 decimal places. Anything else, especially when dealing with small numbers, I like to go at least 4. Right? Here I went 5, but at least 4 minimum. Anything more than that, I think is more than enough, right? But try to go at least 4 decimal places out. Right? Okay. So now we have this, and then on the right side here we have 1,000,006 times 0.05 divided by 12. Okay. And on the left side, we have 4,166.667. All right. All right, and actually, let me keep the number of decimal places the same here, just so it's hopefully less confusing. So here I went 5. So here we'll go 3, 4, and the last one will be 5. Okay. All right. So that is our first step. And again, notice after that first step, hopefully the goal is to isolate n. So I'm getting one step closer to it. All right. Remember, the n is all the way inside those parentheses there. And I can't just jump right into it, right? I got to go one step at a time, each step working my way closer and closer to that n. All right. So the next step here is going to be, I'm going to eliminate this 2,500 by, since it's multiplied, I'm going to divide both sides by 2,500. Okay. All right, so divide by 2,500. So I'm going to take this quantity, 4,166.1234.7, and I'm going to divide that by 2,500. So if I do that, we get okay. Okay, any questions so far? No, the most straightforward way to be to cancel out the fraction and then go from there. Let me take a step back here. I think I made a bit of a mistake here in the problem. I remember now the last time I did this, it wasn't working out for me. Okay. Okay, I'm gonna take a step back. I'm recalling now the last time I did this, I ran into some problems here. And I'm gonna, the problem is a bit faulty. I'm gonna change one thing here in my notes. I'm gonna change that to, instead of 2,500, I wanna change this to 5,000. Okay, so I'm sorry about that. I just remembered here now. It's not gonna change too much what we've done here. A lot of the stuff we've done is all good, except the last step there. So that'll be 5,000. This will be 5,000. And then the last division would be by 5,000. So sorry about that, but I remember here that when we did this case, we got a result that was kind of strange. And I want to make sure that doesn't happen. Okay, so sorry about that. Let's say that you wanted to live very comfortably. So instead of 2,500 a month, you want to live off of $5,000 a month. Okay, I want to find out, all right, how long would this last you, the $1 million, if we are living off of $5,000 a month? So let me do that last operation here. Divided by 5,000. Okay, so now we get Here we have, now this becomes 0.833, and I was going what, 5 decimal places. Okay, all right. So again, notice here, so far, so good, right? Each step of the way, we're getting closer and closer to my goal, right? Which is to isolate the variable n. So the next step, again, you can't just jump to the end, right? We have to account for all these things that are in my way here. The next thing I'm going to do here is I'm going to subtract both sides by 1. All right. Okay, to get rid of that 1. So now that means that when I do that, this goes to 0. So on the right side, I'm left with negative . And then on this side, I'll have 0.83333 minus 1. We're going to be left with negative 0.1667. Okay. All right. Any questions so far? All right. So before, yes. All right. So now from here, I'm going to multiply both sides by a negative 1 just to have both sides to be positive. So here I'm going to go into a new sheet of paper here. So I'm going to multiply here both sides by negative 1 by negative 1. So we get 0.667 equals to 1.00417 raised to the negative 12. All right. So now here is where we kind of come to a dead end with all the other techniques that we've learned in this course so far. Right? It's in the exponent. I can't divide by the negative 12 because it is a repeated multiplication. It's an exponent. So I can't do that, right? So when we get here, we're kind of, we need a new tool, and new to us, right? All right, so the tool that we're gonna need here is I would like to remove the exponent, and I would like for it to not be an exponent anymore. All right, so that new tool that allows me to do that is what is called a logarithm, or sometimes referred to as a log. Right. Now, if you let me bring up our calculator here. If you look at here on the first column of buttons, starting with the second, right, we see that button log right there. And ln is what's referred to as the natural log. When it's written out as log, it's assumed that it's log base 10. And it, for really any purpose, it doesn't matter which log you choose to use, as long as you use it consistently, right? Now, for our case, right, this new function log, why is it important for our case here? Well, the log has a very nice property here, where if you take the log of any number that is raised to some power, that is the same as taking that exponent and writing it in front of the logarithm like a coefficient. All right, now let me show you on the calculator to tell you that these two are in fact the same number. All right, so if I look at the calculator here. All right, so let's say I calculated log of 7 squared, which is 7 squared. And we get this value here, right? Now, let me do the calculation 2 times the log of 7. And you see here, it's the exact same number, right? So this log has the very useful property in an equation like we have in front of us. is that you can take an exponent and instead of making it an exponent, make it a multiplication problem. Now, why is that helpful here is, well, now I can actually solve for that n rather easily, right? So let me switch over here to my notes here. So we could say, so I could show you what we're gonna do when we come to the point here where we have a variable in the exponent. All right, so once we're here, we're gonna use our new tool, right? Once we're at this point here, where the variable is in the exponent, we're gonna use our new tool, and that new tool is you're gonna take the log of both sides of the equation. That came from up here, subtracting 1 from both sides of the equation. So it came from our first division of 5,000. Then that gave me 0.833, and then to subtract 1, and that's where that came from. Okay. All right. Okay. Any other questions so far to this point here? Okay, so now let's use this useful property of the logarithms. I'm going to rewrite my equation. And I'm going to use this property displayed up here. Whatever the exponent is, I'm going to rewrite it as a coefficient. Okay, and now notice how now I've really helped myself out here. Now it's simple, right? Now, now I can isolate that n here by, this is just multiplying numbers. Remember, the way you want to think of the logarithm, it's just a number, right? It's like a function, it performs some operation, right? So, but really you can treat it as if it were just any other real number. All right, so I can, at this step, I can divide both sides by -12 and log of 1.00417. All right, now why do I want to do that? Because that makes this 1, that reduces to 1, and I have exactly what I want on the right side. The letter for the value for n, right? Now the next thing is, let me calculate the left side, right? So I'm going to bring my calculator up here. Okay. And again here, so clear, and I'll plug in log of 0.16667, and I'm going to divide that by, let me open up a set of parentheses here, -12 times log of 1.00417. All right, and I'll hit enter. Okay. So that gives me this number, 3.588. 35 point. And here, I'll just go 1 decimal. And again, the reason for that is n represents the number of years. And really, if you want, if we're talking about years, you can just round up to the nearest year. This is roughly about 36 years, right? So here, let me put the units now, years. So if we have $1 million at the end of our retirement, right, and we have an account that earns interest at, what did we say was 5%? Then $5,000 per month would last me about 35.9 years, all right, or roughly 36 years. Okay, and again, if you wanted it to last you longer, you can, and you still have that same million at 5% interest, you could reduce the monthly withdrawal, right? You can live on less money. All right. Now, one thing on this problem, what I recall now is that the reason 2,500, why I changed that, is you would actually never run out of money in that case, right? Your interest is going to be greater than the monthly withdrawal. So you could live 50 years past your retirement if you have this same setup here, and you still have over $1 million, right? That's kind of why I changed it. I remember why that problem didn't quite work, which is actually ideally in the situation you would like to be, right? You'd like to be able to live off of your interest and not really touch that principal amount. Okay, any questions on this problem here, or the way that how we use the log? The log has lots of other wonderful properties, and it's used in a lot of different applications. But for our application here, we use it to remove the exponent and make it a multiplication problem, which is a very useful tool here. Oh, excuse me, sorry, thank you. All right. Okay. All right. If there's no questions, why don't we end here for today? We have homework due today, so make sure to get that